thank you very much for coming. Thank you very much for this invitation. So this talk will be about something that I try to do on my day-to-day work, which is about how can we weigh dark matter in galaxies. And I will also talk first about how do we know there is dark matter, for starters. And as you will see, as we have also seen already in the nice talk by Nienke, the story of how we came to these discoveries happens right here in the Netherlands.
Bottom one. I find it really confusing.
Excellent, thank you. So, allow me to start by saying that there are more than 200 billion galaxies in the universe. So astronomers sometimes get bored, they have lots of time, they start counting galaxies, and it turns out there are around 200 billion of them. So galaxies are everywhere, and the best example of this is this image that you can see in the background. And this is one of the deepest images ever taken by humankind. It was taken by the James Webb Space Telescope, and every single thing that you can see in this picture is a galaxy. Now perhaps for us today it's very obvious that we can see these galaxies because of the light that is coming to us, but if we take into account for how long have we humans been here on Earth, this knowledge of the fact that galaxies are made of stars is very recent. In fact, only 500 years ago, Galileo was using a telescope to see things that we couldn't see by eye. Now actually Galileo heard about this invention, he heard about some Dutch glass makers in the south of the Netherlands were polishing lenses to see very far away, and the very revolutionary thing of Galileo was that instead of thinking, how do I use this to kill humans, as many people were thinking, how to give this a military purpose, he said, how can I use this to understand about our place in the cosmos? So this was really the revolution that Galileo started, trying to see what was out there beyond what our eyes can tell. Now we have come a long way in these 500 years. So today we have huge ground-based and space-based telescopes like the Hubble Space Telescope, the James Webb Space Telescope, that can take wonderful pictures of galaxies like the ones we can see here. In particular, these two examples are what we call these galaxies, and you can see why we call them like that, because the distribution of the stars is really confined into a very narrow plane. Sometimes we call them spiral galaxies because they develop these beautiful spiral patterns. Now, what is the most famous of all the spiral galaxies? It's the Milky Way, right? And today, we pretty much know that the Milky Way is a spiral galaxy, it's a disk galaxy, but again, this knowledge is fairly recent. And it was essentially, the first time that was quantified was around 102, 103 years ago by this person there on the bottom corner, and the name was Jacobus Kapteyn. He wasn't blue in reality, but if you visit Groningen and you go to the University Museum, you will find a very big mural of him. He's a very important person for the city of Groningen because he was the founder of what eventually became the Astronomical Institute. So what Kapteyn did was essentially making a map of all the stars that he could see in our Milky Way, and he realized that they were really distributed in a very thin plane, and that's how he really quantified that our own Milky Way is a disk galaxy. And these galaxies are crucial for our understanding of dark matter. Now, as Nienke mentioned, already in the times of Kapteyn, even a bit before, astronomers were thinking, is that it? And I think this is again quite a revolutionary question, because if I see this chair, I don't think, is there something else? Is that it? So this idea of really wondering if there is something beyond what we can see, I think it was really revolutionary, and it led to very interesting answers. Now it turns out that galaxies are much more than that. In particular, astronomers believed that there had to be gas because these stars should form from some gas. But this gas was not detectable. And again, we should think about this detection to Dutch astronomers. And in particular, to these two gentlemen here. The first of them you now know very well, Jan Oort. Jan Oort had been a student of Kapteyn in Groningen, then he came to Leiden, became a very famous professor, and he had a PhD student when he was younger, called Henk van der Hulst. Now, what they realized in the PhD thesis by Henk van der Hulst was that this gas, if it was there, it should emit at a specific wavelength, which is around a wavelength of 21 centimeters. Now, crucially, this emission cannot be seen with optical telescopes, so this was the main point of these Dutch astronomers, that they realized that this emission was only observable with big antennas, with radio telescopes. Now, Eventually, the Netherlands became the world-leading country doing radio astronomy. So if you travel around 190 kilometers to the north, you will go to Dwingelo, and you can see there one of the most important radio telescopes in the history of the world that was crucial to understand what dark matter is. And the reason why it was crucial was because thanks to this prediction and thanks to this type of technology of radio telescopes, astronomers found that galaxies have huge disks of gas. And in particular, the gas that we can see more easily is neutral atomic hydrogen. Now, when I say huge, I really mean huge. And an example of this is this image. So we have on the right-hand side the picture of a nearby spiral galaxy. You can see the very beautiful spiral pattern. And then on the left side is exactly the same galaxy at the same physical scale, but we can see the distribution of the gas. So especially if we overlap both of them, it becomes very clear that this gas is much more extended than the distribution of the stars. And this is great because it allows to really observe dark matter. Now, astronomers had already built telescopes, so they saw that there was more than what our naked eye could see. Then they found this gas, so they saw it was more than only the stars. But they didn't stop there, and I asked again the same question: is that it? And again, the surprise was quite surprising. Now, they figured out a very clever way to understand if there was something else right there, because they found that these galaxies rotate. And depending on how fast these galaxies are rotating, we can infer the mass, because essentially, as we were also seeing in the nice talk from Nienke, how fast a galaxy rotates is going to depend on how much mass there is and how far are you from the center of the galaxy. So in principle, if you have a lot of mass, there should be a fast rotation, and the farther you go from the center of the galaxies, you should rotate more slowly. So we can see this in this movie. So if galaxies rotate as we expect them, they should look like this. As you can see, most of the mass, most of the light is in the center, so the center rotates very fast, the outer parts go very slowly. If we had observed this, everything would have been perfect, but this was not what we observed. Instead, the observations are more to what we see on the left-hand side. So as you can see, first of all, the overall rotation of the galaxy is much faster than what we were expecting. And the outer parts of the galaxy are not rotating any slower than the central parts. If anything, they can rotate faster for many galaxies. So this tells us right away that there has to be some mass that we are not accounting for. Now, the way in which I usually visualize this is with this type of plot. Not as cool as the movies, but it also has the same information. So essentially, in the vertical axis, we can see how fast are the stars or gas in a galaxy rotating, depending on how far you are away from the center, right? So these were the same type of plots that Nienke was showing. And as you can see, for instance, for this galaxy, the central parts rotate at these moderate velocities, and then the outer parts rotate much faster and more or less at the same constant speed. A quick parenthesis here, in case you haven't thought about how huge are these distances and these velocities. So this galaxy has a moderate velocity. Typically, there are many more galaxies rotate faster than this. And yet, just for reference, this moderate galaxy rotates at a speed which is around 1,500 times faster than what a Formula 1 can go at top speed. And to reach from the center to the outer parts of this galaxy, which is around 4 billion times the distance between the Earth and the Sun, it will take Max Verstappen in the fastest car around 150 million years to make it up there. So whoever is your Formula 1 driver, they wouldn't be very happy to have to do this trip. Now, as we were seeing before, what we were expecting was something more like this blue line. Something that is faster in the center because you have more mass, then you go farther away, the velocities decrease. And right away we see this huge mismatch in velocities, and this tells us right away that there has to be some invisible mass that is missing. And this mysterious mass, in lack of a better name, we call it dark matter. So, rotation curves of galaxies, and in particular, gas rotation curves in which the Netherlands played a major role thanks to the radio astronomy, are one of the most conspicuous pieces of evidence for the existence of dark matter in galaxies. So now that we know there is dark matter, the question is, how can we weight? How do I know how much dark matter there is in galaxies precisely? And this is something that I do, or that at least I try to do at work. So I will now guide you through one of my days at work in the Leiden Observatory. So So I arrive in the morning and I have the rotation curve of this galaxy, where I know that I need dark matter to explain the velocities. So I put a bit of dark matter, and the idea is I will put dark matter, together that dark matter with the stars and the gas should reproduce the observations. So I start putting a bit of dark matter. So I put some dark matter, then I put it together with the stars and the gas, and the total contribution of those two is the red line. So as you can see, the red line is not matching yet the observations. So I put a bit more dark matter. So I got closer, you can see now the contribution of the dark matter grew, the total velocity grew, but I'm still falling short from the observations. At this point I got tired, so I go to grab lunch, I go for a walk. When I come back to the office, I don't want to be doing this forever, so I put much more dark matter. So if I get too impatient, you see that it doesn't work very well, because now I put so much dark matter that the total velocity is much higher than the observations. So I spend my afternoons playing like this until I find the exact amount of dark matter that this galaxy needs so that I can explain the observations. Don't tell anyone that this is my job, because they might fire me when they realize how easy this is to do. But it's fun to do, which is why I like it. So in this way, we can weigh dark matter in galaxies. So if you realize, we're really using the motions of the stars and the gas in galaxies in order to balance as a scale to understand how much dark matter there is. Now, we can do this for many different galaxies. We can measure how much dark matter there is. And the surprising result is not only now that there is dark matter, but is that the vast majority of mass in galaxies is dark matter. 50% of the mass, more or less, is in the form of stars and on gas, and the other 85% is in the form of this mysterious dark matter. So it means that we should really abandon this idea of galaxies as being a collection of stars and gas just right there, to understand that they live in massive, very extended dark matter halos. I think this is quite mind-blowing. There is something else that every time I think of keeps me surprised. We are using the visible component of galaxies, so the stars and gas, to map the distribution of huge dark matter halos that are much more extended than what we can observe. But we don't stop there. We use the properties of these huge dark matter halos to then go back to smaller scales, to really microscopic scales, because depending exactly on what dark matter is made of, so depending on what type of particle constitutes dark matter, the distribution of the dark matter inside this halo is going to change. So we can really use galaxies at these astrophysical laboratories to understand what dark matter is made of. Now, in the last couple of minutes, I want to show you an example of this. So one of the favorite theories of current day astronomers is that dark matter is cold. And this name is very bad, but what it means is that the dark matter particles move very slowly between each other, and they only interact through gravity. So they don't radiate emission to each other, they don't collide with each other, they only feel the pull and push of each other through gravity. Now, if this is the case, we expect the dark matter halos to show some properties. In particular, we expect a correlation between two parameters of the galaxies that are very simple to understand. One of them, in the horizontal axis, is the mass of the halo. So how much total mass in dark matter is in a given galaxy. And then on the vertical axis is how concentrated is the dark matter. So something with a high concentration has a lot of dark matter in the center. Something with a low concentration is more diluted, so the dark matter is more spread out. And according to our theories, if dark matter is really cold, galaxies should lie on top of this line. And the nice thing is that when we go and we do our observations, it turns out that galaxies are right there. So when something works this well, astronomers get both happy and confused. But the overall conclusion will be that dark matter is cold and that now we understand everything. That wouldn't be good, because we astronomers will be, at least I would be left without a job. So it turns out that actually the story is not so simple, which I am grateful for. So in particular, in this last minute or so, I want to introduce you to a population of galaxies that might be telling us something else about the nature of dark matter. And it's a type of galaxies that I studied a lot when I was doing my PhD, and they are called ultra-diffuse galaxies. Why are they peculiar? Well, because we're used to seeing very big galaxies that are also very bright, or very small galaxies that are very faint. And these ultra-diffuse galaxies are some sort of weird thing in between, because they are very large, but they are very faint. We can actually see through them, so that's why we call them ultra-diffuse. Now, in my PhD thesis, when I was young and happy, I was trying to see where would these galaxies lie in this relation. And what we were expecting, if dark matter is cold, is that these galaxies lie right there. Instead, what we were finding is that these galaxies shift down this relation. And of course, this is very surprising because this is in tension with this idea of cold dark matter. So both me and my supervisor panicked for a while until we convinced ourselves that these results were really there and we're trying to understand them. We're still trying to understand them, but this is very exciting because, as I was saying before, depending on exactly on what dark matter is made of, like the names we saw before, cold dark matter, hot dark matter, warm dark matter, self-interacting dark matter, all this just means different properties on these dark matter particles. So depending exactly on what they are made of, the distribution of the dark matter halos is going to change. So we can use the type of extreme galaxies, like ultra-diffuse galaxies, to really map the properties of the dark matter particle. So with this, I come to my conclusions, and we still don't know what dark matter is made of. However, we have a very robust way to weight this dark matter. And every day we keep discovering new galaxies, we keep developing new technology that makes me very hopeful that soon we will be able to constrain its nature. So I really hope that if in a few years you invite me to give a talk again, we all meet here, this talk will not only be about how can we weight dark matter in galaxies, but also about how can we really constrain the nature and finally be able to answer a question that has puzzled astronomers for about a century, which is what exactly is dark matter made of. Thank you very much for your time.
Thank you very much, Pavel. I'm happy to see that when you think of a Formula 1 driver, you think of Verstappen instead of Perez. Let's see if you're ready for a while. Any questions?
Is there any indication that the dark matter is unequally distributed across the halo, like for instance the ripples that you see in the spiral arms of galaxies?
Well, in principle, the idea is that the distribution is not very granular, it's more or less homogeneous. We tend to have more dark matter in the center, so the density decreases with radius, but the idea is that it should be homogeneous precisely because if it was made of clumps, we should be able to detect movements of stars or gas being abnormal. And it is related somehow with why the spiral arms form indeed, because so what we see as spiral arms are not rigid structures that are rotating across the galaxy, right? So these are more like a density patterns that form there because of the underlying mass distribution. So if you were to, I think if dark matter, if the distribution of dark matter was more granular, more concentrated in big groups, right, and homogeneous, we will expect to see a different pattern in the spiral arms of galaxies.
Thank you for your talk. Did I understand correctly that you're trying to fit the data to one of those curves of the particles?
Yeah, so currently that's what we're trying to do. So essentially, as I was saying, depending exactly on what are the properties of the dark matter particle, we're going to expect the distribution to change. And so now what we're trying to do is trying to collect more data of this type of galaxies to see exactly where do they lie in this type of plane, and then we compare against models that predict where these galaxies lie in this relation. So
could it be a combination of those two, or is it definitely only one of those things?
You mean if dark matter could be made of different, if there could be different types of dark matter? Yeah, I mean that's certainly a possibility. Most of the models assume that whatever the properties of the dark matter particle are, all dark matter particles behave the same. But it's certainly a possibility that there is even a diversity in the properties of the dark matter particle, and perhaps there are two different particles. So, yeah, that's also a possibility.
Do we know why dark matter particles don't emit black body radiation?
Well, we know they don't. So they don't lose when they lose energy, they don't emit radiation. Why they don't do it, I think, is really at the core of the question of what dark matter is made of. I don't think I have a better answer for you at this moment. So we know that they don't emit at any wavelength. Yeah, but the why, yeah.
First, I want to say that I'm not from an astronomy background, so perhaps what I ask is completely off the book. But you said that dark matter is homogeneous. But in the beginning, you described it as something that actually creates a gravitational force that keeps these patterns on the galaxy. If it was homogeneous, would you not pull those patterns towards the center of the galaxy also, instead of just forming these rings? Would they just break in time?
So what I mean by homogeneous is that the distribution is smooth. So you have more dark matter in the center and the center of the galaxy, and as you go farther away, the density of dark matter decreases, but relatively in a smooth way. So what I mean is that if you were sitting in the center of the galaxy, you will see a lot of Milky Way right there. And then you start walking, you will see less and less dark matter, but gradually. It wouldn't be that you walk a bit and a lot of dark matter. You walk a bit more, very big dark matter, and then a lot, and then so that's what it means. It's like it's a smooth distribution, and that's, I mean, we didn't know that, right? So the fact that it has to be this smooth distribution, I mean, we came to this observation based on this rotation curve, because if you don't have a smooth distribution, you can explain that easily how fast the gas and the stars are rotating. So I wouldn't be able to get that match that I was showing before between the rotation curves and the red line that I was showing.
Yeah, I don't quite understand what you said, because in the talk on Nienke, she explains, if I understand it well, that the amount of mass is increasing if you go further from the center of the Milky Way. So the amount of dark matter increases, is not decreasing.
Yeah, that can be a bit confusing. Let me see if I have a nice, no, in which direction I'm going. So, almost there. No, I was going in the wrong direction. So what we know is that, so dark matter, so for example, if we look at the stars, most of the stars are in the center of the galaxy, and when we go out, you have fewer and fewer stars. And essentially, well, this has to do with how galaxies form, and eventually most of the mass in the center because of gravity, so you always end up with the concentration of the mass in the center. So with dark matter is the same, because gravity is the same, so you have more dark matter in the center. Now, if I manage to get there, and I think I'm very close, excellent. So this shows a bit of a sketch of, again, this is like more or less what the rotation curve that we measure, and this is the mass that we will expect based on the stars. As we can see, because we have most of the mass in the central parts, we have more velocity from the stars here, and then when we go to the outer parts, the velocity starts decreasing. So the thing with the dark matter is that if we were to have here a picture of dark matter, that it will be much more extended. So it will be so extended that even when we go to these parts, you still have a lot of dark matter. So that's why we can manage to explain these flat rotation curves. Now, in the central parts of galaxies, so it's hard to explain because I don't have the equation, but in the central parts of galaxies, even though we have more dark matter because the density is concentrated in the center, the contribution to the velocity doesn't peak right in the center. And this has to do with the exact way in which the density is distributed. So the contribution of the dark matter, even though you have more density in the center, peaks later in the, at a later radii. So yeah, the contribution of dark matter, we can see it in the outer parts of galaxies, even though the mass is distributed similarly to the stars. Most of the mass is in the center. That has to do with the geometry of the system.
You can derive the radial density of the dark matter from these curves, I think.
Absolutely. Yeah, absolutely. Someone was asking before if there was like a, if I understood correctly, if there was dark matter like around, so it's very easy, well not very easy, but there is a way to calculate the dark matter density, for example, around the solar system. You can came up to, I don't remember the number, I can look it up and I can let you know, but there are like how many dark matter particles per second more or less are crossing through us right now, and it's very few. The densities are not very high in this part. But yeah, you can estimate how much dark matter there is in different parts of the galaxy. Yeah.
Okay, thank you very much, Pavel. Let's thank him again.